Hello everyone, thank you for attending this presentation. Today, I will present our work titled Weighted Codebook Scheme for RIS-Assisted Point-to-Point MIMO Communications, published in IEEE Wireless Communications Letters. This study addresses the challenges of optimizing RIS reflection coefficients in MIMO systems by proposing a novel weighted codebook design. Let me guide you through the content of the slide in detail. The presentation is structured into 5 sections: background, system model, weighted codebook design, simulation results, and conclusions. Reconfigurable intelligent surfaces have emerged as a transformative technology for 6th generation, enabling dynamic control of wireless propagation environments. However, existing pre-designed codebook schemes face critical limitations that hinder their practical deployment. While these methods, such as those proposed in Reference 3 and Reference 4, offer advantages like low training overhead and reduced computational complexity, they suffer from a fundamental bottleneck: finite solution space. This limitation arises because the optimum RIS configuration often lies between discrete code words in the codebook, leading to significant performance gaps when a single code word is selected. Increasing the codebook size can improve resolution, but this approach escalates payload overhead and computational complexity, making it impractical for real-time applications. Furthermore, pre-designed codebooks inherently lack adaptability to diverse channel environments. The core challenges lies in balancing system performance, training overhead, and complexity. Existing solutions either require a substantial amount of payload overhead and have high complexity, or incur non-negligible performance gaps. Our work aims to resolve this trade-off by introducing a weighted codebook scheme, that is, to design a method to blend code words, achieving near-optimum performance with low training overhead and moderate complexity. Next, we introduce the system model. As shown in Figure 1, we consider a RIS-assisted point-to-point MIMO system with the following parameters. The base station has MT entities. The RIS comprises N reflecting elements, and the user equipment has MR entities. The composite end-to-end channel includes 4 components: the direct channel from the BS to the user, the BS to RIS channel, the RIS reflecting coefficients matrix, and the RIS to user channel. All channels are modeled with ratio fading, incorporating a ratio factor, path loss, and the line of sight and the non-line of sight components. During the uplink stage, the BS receives payload signals described by Y, where X is the payload simple matrix and NBS is the noise at the BS. During the downlink stage, the received signal as a user is given by here, and the W is the BS transmit precoder, S is the transmitted information simple, and NUE is the noise at the user's receiver. The core innovation is the weighted codebook design. Instead of selecting a single code word, we combine multiple code words with the optimized weights. During the uplink training stage, observations are corrected across Q training blocks. For training overhead Q less than n+1, a minimum norm solution is used for channel estimation. For Q equal to n+1, The n+1 dimensional DFT codebook ensures accurate estimation of the channels. Then, we formulate a MIMO channel capacity maximization problem as this. According to reference 5, the above problem can be simplified by maximizing the lower bound of the channel capacity instead, and it can be solved by the fixed point iteration method, where the iterative equation needs to satisfy the KKT conditions. The dimension of the weight vector is reduced from n to q with the computational complexity shown here. Besides, we introduce an environment-aware codeword configuration order, which enhances system performance for low channel overhead scenarios. Next, given the optimum weight vector k, we adopt a singular value decomposition method and a classical water-filling power allocation algorithm to obtain the optimum transmit precoding matrix. Finally, the optimum RIS RC vector can be calculated by the weighted sum of the code words we configured, and we can obtain its corresponding transmit precoding matrix. As shown in Figure 4, we obtain a new RIS configuration phi optim with the codeword weight, and thus the proposed scheme eliminates performance gaps caused by finite codebook space. And here we provide a simple scenario to describe it more clearly. In Figure 2, the blue arrows denote the pre-designed codewords. The red arrow denotes the optimum RIS RC configuration obtained through the channel estimation and passive beamforming scheme. The green arrow represents the RIS configuration obtained through weighting. We can observe that the proposed scheme is capable of finding the optimum solution achievable on the XOY plane by adopting a weighted design on code words phi 1 and phi 2. This significantly reduces the performance loss caused by the finite codebook space. Here are some of the simulation settings. We first evaluate the channel capacity versus training overhead within perfect CSI and imperfect CSI scenarios. We can observe that as the training overhead increases, the proposed scheme gets performance improvement and always outperforms the DFT and random codebook schemes. Moreover, the environment-aware codeword configuration order can significantly enhance system performance for a relatively low training overhead. Then, facing the imperfect CSI scenarios, as the pilot power reduces, the proposed scheme exhibits a smaller performance degradation compared to the random and DFT codebook schemes, indicating its stronger robustness against noise. Next, we can observe a logarithmic increased relationship between the channel capacity and the transmit power at BS, with a low training overhead Q equal to 6. Proposed scheme shows the best performance. Finally, we evaluate the relationship between channel capacity and the number of RIS elements. With the increase of the RIS elements, the channel capacity increases, which is due to the fact that a larger number of reflecting elements could reap more radiating energy by coherently superimposing all cascaded links. In conclusion, we proposed a DFT codebook weighting design for point-to-point MIMO systems, we utilized the observations from the configured code words to design the weight coefficient vector and the corresponding transmit precoding matrix, thereby obtaining the optimum RIS RC vector by calculating the weighted sum of these code words. We considered the impact of different code word configuration orders on the performance of the proposed scheme. Here are some references of the letter. Thank you for your listening.